Okay, so then we can start with our last talk for the day. The speaker is Igor Kukavica from USC, and he will tell us about inviscid limit for the Navier-Stokes equations.
Well, thank you very much for your invitation, and I'm sorry that I couldn't participate in person. So, but yeah, so the purpose of today's talk is to kind of summarize recent results on the inviscid limit. So I'll present in such a way that it's suitable for people who don't work in inviscid limits necessarily. So I'll summarize results, and I'll present the result with Vicol and Wang on a bit later in the talk. So I'll go very quickly over the beginning about the Euler and Navier-Stokes equations, and then I'll slow down. So that is the abstract. The inviscid limit concerns the Euler equations, so which are modeled the inviscid incompressible flow. The initial condition is given. It will always be assumed smooth. Some results allow maybe, yeah, basically for Euler we need smooth solutions. And the basic existence theory is if the solution is smooth enough, for example, if it's in a Sobolev space Hm for m bigger than d plus 1/2, then there exists a smooth solution on a short time interval and with the better results in 2D. So the classical references are Ebin Marsden and Temam, and there are many others. So on the other hand, the Navier-Stokes equations are their viscous counterpart, and there we could consider the weaker concept of solutions. So for instance, if U naught is L2, we have a Lie-Ray's weak solution, as we know, and if the solution, if the initial data is smoother, then one can just repeat the Euler proof and obtain, for example, the local existence for Hm m bigger than d plus 1/2, d over 2 plus 1 as for the Euler. With the time of existence for smooth solutions independent of nu. So the basic question of inviscid limit is whether solutions of the Navier-Stokes equations converge toward the solutions of the Euler equations as the viscosity goes to 0 in some sense, so meaning in some norm. So could also be in a weak norm. And the answer is yes for domains with a boundary. These are the classical references. So some consider the Helder spaces, 2D, 3D. For example, Ebin Marsden already has the inviscid limit, but with high regularity. So D halves plus 2 plus 1, so higher. And I'll state the result of kata for the domain. For non-smooth initial data, there is papers by Constantine and Wu, for example, vortex patches. For the smooth data, so here I state the result of Kato. I'll also use his notation in a later paper that he denotes U a solution of the Navier-Stokes equations. It depends on the nu, but we just omit nu. So when it's just U means the Navier-Stokes equations, and when it's U bar, it means the Euler equations. So in 1972, he proved that if the initial data is sufficiently smooth, so he took m to be at least 3 an integer, then there exists time depending only on the norm of the initial data, but not on the viscosity, such that U belongs to this space, so continuous in Hm and more regular in Hm minus 1. And it's bounded in this space. On the other hand, for the inviscid limit, he proved that the limit exists strongly in Hm minus 1 and weakly in Hm uniform in time. And the Euler solution satisfies same regularity as the Navier-Stokes, meaning it's continuous with values in HM and absolutely continuous in HM minus 1. Masmoudi in 2007 extended the strong convergence also to HM. Of course, you can interpolate and get strong convergence in all H k spaces k less than m, even k is not integer, but to get HM, need to do the splitting method, and so he proved that indeed the convergence also holds in HM. As I mentioned before, for rougher data, one may also get so I'll comment after this proof. So I'll go quickly over the proof of convergence in L2. So if you just take the difference of two solutions, so the solution of the Navier-Stokes and the Euler, and just substitute into the equation, and just do the energy inequalities, then on the right side we only get this viscous term coming from the Navier-Stokes equation, and we can split it into the one for the difference and the one for the Euler. The difference one gives you a coercive term, which you put on the left side, and for the Euler, we may use that U bar is smooth, and if U bar is smooth, we can just so this is here Laplacian. So we can just estimate and obtain then the rate of convergence for V in L2 to be O of nu. For rougher data, we need to integrate by parts here, so we get still convergence, but with a lower exponent, so nu to power 1/2, and turns out to be sharp by Konstantin and Wu for the vortex patches initial data. The above proof does not work for the domain with the boundary because of the mismatch of the boundary conditions. So for the Dirichlet, for the omega, we typically consider the Dirichlet boundary conditions, although it's not the only choice. And if you do that, then the Navier-Stokes equations boundary data is gamma u equals 0, gamma denoting the trace. And for the Euler is the non-penetration boundary conditions. And because of this mismatch, one does not expect the inviscid limit to hold in strong norms in a bounded domain. So n is the notation for the normal. Okay, so if U naught is in the energy space, then in any space dimension, we have a weak solution, and one may ask the following question. So, do solutions of the Navier-Stokes equations converge to the Euler equation in the energy norm? So, is it true that U minus U bar converges to 0 as nu goes to 0 in the norm L infinity L2? So, on the interval independent of nu. So this is a well-known open problem, and so it's still open for the domain domains. So in a domain omega, as I said, if the domain is without boundary, then it's well known to hold. So there are a lot of results, though. So one of the goals of this talk is to summarize those. So we call this the inviscid limit problem. And again, the limit is the answer is affirmative for the domains with boundary. But when we go to the domains with boundary, then even if you take the dimension 2, and even if you take the simplest case when the boundary is flat, it just seems to be as difficult as when you take the most general case. So just reducing the dimension does not make problem any easier. Because of the slip at the boundary, we can so this would be a solution of the Euler equation. This would be, or maybe I should put the Navier-Stokes on the left. So here the velocity vanishes at the boundary. Here it does not. So this limit cannot hold in L infinity and L infinity. But there is nothing wrong with this picture if we are happy with a lower convergence. For example, we can ask in the interior, or we can ask in L2, because this presumably the width of this layer can be nu dependent, and the convergence in L2 could still hold. So Kelliher 2016 proved that if the limit actually in the space L infinity LP is infinity for every p for the vorticity. So for the vorticity convergence in L infinity LP, one cannot obtain the convergence as long as the Euler flow does not identically vanishes. So in the case of other boundary conditions, for example, I call Lyon's boundary conditions when the curl vanishes, so U equals 0, curl equals 0, or more generally for the Navier boundary conditions, more generally, there's a family of boundary conditions which can include both the Navier and the curl U0 boundary condition. Then the answer is affirmative, and here's a couple of references. So for the Navier, Masmoudi-Rousset, and so this is for Berselli-Spirito for U equals 0, curl equals 0. Kato in 1984 proved that there is actually a sufficient condition, and actually necessary and sufficient condition for the inviscid limit in bounded domains. I will speak only about Dirichlet boundary condition. It is that the boundary dissipation, so the energy dissipation in a small boundary, small neighborhood of the boundary. So if this is omega, this would be this is the notation for the omega epsilon, epsilon being this neighborhood. So the condition is that the gradient U squared integral over it over this narrow width, it's very narrow because it's of the size C naught nu. This quantity multiplied by nu needs to go to 0 for the inviscid limit to hold, and vice versa. If it holds, then the inviscid limit holds. This seems optimistic because the band is so narrow. However, nobody has been able to prove that this holds. And in fact, this condition tells you the scenario how the inviscid limit fails is if some gradient of the velocity is very large in a small neighborhood. So for example, some bad things coming out of the boundary into the interior. So for the inviscid limit to fail, something violent should happen close to the boundary. In addition, Kato proved that this condition and the strong limit to hold is equivalent for the U of t to converge to U bar of t L2 weakly. So the weak convergence is necessary and sufficient for the inviscid limit to hold, which is again kind of bad news, which tells you that even if you're happy with a weaker topology, that does not make things easier to prove. So it's equivalent to prove weak convergence or strong convergence. And that's just a very simple argument, based on this. So the proof for Rn does not work. The main difficulty is actually the Laplacian term, because in one of the terms we just integrated by parts and we obtained the coercive term, but here we obtain a very possibly very large non-negative this boundary term, which could be of the same size as the main ones. So the problem is this boundary term resulting from the viscosity. So just one-page proof of the Kato's criterion. The correct proof should be longer, but this is the sketch. So here is the proof for the half space, but it can be adapted very easily to curved domains. So what we do is we correct the Euler flow in such a way that it vanishes at the boundary. So we introduce a corrector, phi1, And there's a lot of freedom how to choose this corrector. So we want to choose it in such a way that it agrees with the Euler flow at the boundary. So here is the picture when x1 is constant. So this is x2. So this x2 and so this is for fixed time and fixed x1. So as you go to the interior, you start with the negative of the Euler flow to cancel the Euler flow, and then you go inside, and it's an advantage in the proof to have it compactly supported. We also want phi to be divergence free. Therefore, we compute phi2 to be the integral of the d1 phi1. And since we do not want phi2 to grow inside the domain, we actually require phi1 to have average 0. So this part should cancel with this part. But the important thing is that everything is happening on some size close to the boundary of size alpha. And for now, alpha is arbitrary. So then you write the equation for the difference between the Euler and the Navier-Stokes. And then you test it with Navier-Stokes minus Euler minus the corrector, because this one has the average 0, and then Laplacian you can integrate by parts. So since this vanishes on the boundary, you get two main terms. One comes from the dissipation, one comes from this, and these are the main terms because they contain d2 phi1. d2 means the derivative, so phi1 has to quickly change sign. So because of this, d2 phi1 is large, and then this is the reason why these two quantities are the largest. So one comes from the viscosity, one comes from the bilinear term, and in both you apply Poincaré type inequalities. Especially here, you go from u to the gradient, and that's the reason that the second one requires alpha to be small because we use Poincaré, and the first one requires alpha to be large because of d2 phi1. So then you choose an optimal alpha, and the optimal alpha is a constant times nu. In which case you get from here you get this term, and from here you get that term. And this is not a problem that it's a power 1, so you can do the Helder inequality. But basically, you need to assume that these two quantities are small after integrated in time. And this is the proof of Kato. All the other terms, there are many, are more easier controlled because they contain phi2, which is much smaller, or first derivative, which is smaller. So based on this idea, there have been a lot of different sufficient conditions, which actually were very helpful in many ways in different theorems. So here are some, and there's some I cannot state all the known ones, but Xiaoming Wang's condition is on the tangential component of the velocity. However, the boundary layer is larger, so you need to divide by quantity which goes to 0 as viscosity goes to 0. This is O1 with viscosity. Then Kelliher proved that the Kato's condition is true if you replace gradient u with the vorticity. So this tells us that for inviscid limits to fail, large vorticity has to be created at the boundary. Then the other two boundary conditions, boundary criteria by Kelliher are, for example, this one, which tells you that the H-1 type convergence of the vorticity, and Bardos TT also the tangential component of the vorticity has to go to 0 in some sense as goes to 0 for inviscid limit to hold. Then Konstantin Gindi Ignatova Vicol is equicontinuity of the quantity u1, u2 as nu goes to 0 close to y equals 0. We also had the sufficient criteria based on monotonicity. So monotone data are very important for the Prandtl equations, about which I'll speak in a bit. So our condition says if the velocity, first component of the velocity of the Euler equation is bounded by 0 from below on the boundary. And the trace of the, so this is the conditional result, because the trace of the Navier-Stokes equation is non-negative. So that's the monotonicity, this is the monotonicity assumption, but we require curl to be non-negative. So if the curl of the Navier-Stokes equation is non-negative, then the implicit limit must hold. This condition can be relaxed to allowing even a very large bound, so 1 over nu. So even if the bounds are very large in the sense that this has to go to 0, then the implicit limit holds. However, if one really wants, even in 2D, to bound the vorticity from below and above, the bounds tend to be exponential. So the difference between what is available and what one can prove is now between exponential and polynomial. But yeah, even this kind of large lower bound would allow the implicit limit to hold for monotone data. There are by now also quite few unconditional results for the implicit limit. So the initial work was by Sammartino and Kaflish in 98 and in 98, two-part paper. First one concerning the existence of solutions, second one the implicit limit. So they proved that implicit limit holds if the initial datum is analytic. And would like to emphasize this is YDY analyticity. So we are not trying to make the data small in any way close to the boundary. So it's YDY analyticity or analyticity in a wedge. So so the main tool for analytic data is that they prove that the validity of the Prandtl expansion holds in the analytic spaces. And their main device is the abstract Cauchy-Kovalevsky theorem. So the energy method proof was also obtained by Wang, and Zhang later on. So Maekava took a different viewpoint, and he proved in his paper that the implicit limit holds if the vorticity is supported away from the boundary. So if it vanishes close to the boundary, then the implicit limit holds, but it does not have to be analytic. So Nguyen and Nguyen, so Tuan and Trinh Nguyen, gave an alternate proof of the Sammartino-Kaflish in 2017, which does not use Prandtl correctors. And the idea is to use much more suitably adapted norms. So the L infinity, LN1 type norms with analyticity. But it's the same result as Sammartino-Kaflish, so for analytic data. So with Vlad Vicol and Wang, we proved in 2019 that the implicit limit holds if the initial data is analytic only close to the boundary and Sobolev away from the boundary. So this this contains both of these results because Sammartino-Kaflish is analytic all the way in, and Maekava's, if the vorticity vanishes close to the boundary, then in particular is also analytic. So it would be a general result for the implicit limit to hold. So analyticity is required only close to the boundary, and again, it's a YDY analyticity. And Fei proved a 3D version of this analytic Sobolev result. Since then, there has been developments. So Bardos, Nguyen, and Titi proved for curved domains that if the initial data is analytic close to the boundary and Sobolev away, then the implicit limit holds. And Nguyen just recently also proved it for the exterior of the disk. There are other unconditional results. For example, Gerard Varey, Maekava, Masmoudi, for perturbations of the shear flow. So if it's a certain perturbation of a steady profile, then one can actually even obtain the Gevrey-2 norm type convergence. And there is also Gie, Kelliher, Lopez, Mutsukato, and Sensweig-Lopez, who proved the inviscid limit for different flows with symmetries. So circular symmetric flows, plane parallel, parallel channel flow and the parallel pipe flow. And these are flows where the pressure is zero, but the inertial term is not zero. So also there is a review paper for up to 2018. So it's for people who are interested in the inviscid limit problems. It's summarized nicely in this review paper. So in the remainder of the talk, I'll just sketch some ideas from our result with Vlad and Faye, and also talk about Prandtl, and at the end, time permitting, I'll talk about the basic existence of the Prandtl equations. So the initial work, the seminal work of the field by Sammartino and Kavlish, utilized the Prandtl equations, which were designed to model the flow, inviscid flow close to the boundary. So the idea is to say, okay, let U be the first zeroth order approximation for the first order approximation plus error. The zeroth order approximation should be the Euler equations, and we seek the first order perturbation to be to have this scaling y over epsilon in the spirit of Prandtl, requiring that the data is divergence free, gives us that epsilon must be of the order square root of nu. So epsilon is always the notation for the square root of the viscosity. So if you replace these ansatz into the Navier-Stokes equations and match the terms of the lowest order terms, those which remain after Euler, we obtain that this first order approximation, which is U tilde V bar, satisfies some boundary condition. So U is the x component, so the first component of the velocity. This is the second component. So the first component does not vanish, and the second, and it coincides with the Euler trace. And turns out that the U tilde V bar satisfy a Prandtl-like equation. It's not exactly Prandtl equations because we get also the first order terms. Yeah, quite few. And V is obtained. So there is no evolution equation for V. V is obtained by integrating the x component of the velocity. Again, these are the boundary conditions I stated before. And to homogenize the boundary value at y equals 0, which makes the Prandtl equations more amenable to study. So we change the variable, so just homogenize at infinity, homogenize at 0, but of course this makes the infinity then non-zero. So if you do that and normalize also the second component of the velocity, we obtain the classical Prandtl equations. So which the main part is looks like the heat equation, but it's not. It's just a derivative in the y variable, and the inertial terms are similar to the Navier-Stokes, but the pressure is given. So we only have the evolution for the first component of the velocity. The pressure is given, and the second component of the velocity is computed from the first component by integrating dx. So of course the Prandtl equations already contain a difficulty, which is the derivative loss in the x direction. So if you imagine this Vp being here, we have a dx up hidden under the integral. So it seems like it's a one derivative loss. Due to recent work, turns out that it's actually less than one. So the Prandtl, and I'll speak about it later on. So that's the result of okay, I'll speak at the time Dieter. So with the boundary conditions are now homogeneous at 0, but UP matches the L infinity at matches the Euler flow at infinity. So then expanding the error, meaning introducing the error, which is the Navier-Stokes minus Euler minus Prandtl divided by epsilon, we obtain a set of complicated equations derived by Sammartin and Kaflish for the error. And the features are we get linear terms, we get Navier-Stokes type nonlinear term, the pressure is not known, and quite few forcing terms. Of course, for V similarly. So again, same feature, so additional linear terms, nonlinear term, this is the Navier-Stokes, and forcing terms, divergence conditions, and another problem is non-homogeneous boundary conditions for the vertical velocity. And then their proof is obtained of the vanishing viscosity by analysis of the error equations in analytic spaces. But it does not work quite yet. So additional problem is that the L2 norm is not strong enough to analyze. So they do further Prandtl expansion of this. So it's a very complicated proof and pretty amazing. So the boundary term for the velocity is G, G, which is the integral of the derivative of the first component. The forcing, the specific form doesn't matter, just wanted to state them for completeness. But yeah, so the analysis of the terms is kind of, you have to do it in analytic spaces, but U bar close to the boundary cancels epsilon, and then there is a decay due to Prandtl. So close to the boundary, this term cancels epsilon. Further away from the boundary, the Prandtl is decaying. So this term is under control in a very complicated space, but that maybe gives you some, one of the ideas of the proof. So the, yeah, as I pointed out, you get a lot of Euler and Prandtl terms, and the proof is obtained by further Prandtl expansions of the error equations. So whether the Prandtl equations actually are equivalent to Prandtl expansions are equivalent to the validity of inviscid limit, it's not known. But there are some results which indicate that the Prandtl equations are unstable. So Prandtl expansions are unstable. So the Prandtl expansion cannot be holding in L infinity by Grenier and Wang. So this gives you, on one hand, some idea which norms to use, but on the other hand, tells you that maybe Prandtl could be a problem in Sobolev spaces, or actually inviscid. The whole inviscid problem might be problematic if you think that the Prandtl is the correct expansion. So, okay, let me state the result with Vlad and Fei on the analyticity close to the boundary. We had two papers. So in the first one, we had two norms, L infinity based and L1 based. In the second one, which is to appear still, we have two norms, so L1 based analytic norm and the Sobolev norm in the interior. So to state the result, I need to introduce the norms. So I will state our second result where we have the L1 norm. The domain is diamond shaped, so this is a very, very small angle. In the when one does analyticity to the boundary of any type of parabolic equation, like of heat type, let's say. So if you take heat equation and try to put analyticity, it turns out that tangential, it has to be done in a wedge. So this wedge with a smaller, small angle. So this actually comes from the heat equation reasons, that this angle has to be small. Then the analyticity radius is growing up to the up to scale 1. so this could be, of course, a number, but we take one for simplicity. Any viscosity independent number works. So analyticity grows. This is the analyticity in Y, and then it goes under 45 degrees to 1 plus mu. It's not like the solutions are analytic up to a certain point, and after that they're Sobolev. So it's kind of a transition period. So because of this, the norms have to be kind of supremum based, supremum on the interval, certain interval. In fact, if you evolve the Navier-Stokes equations for a short time, you kind of expect the solutions will become analytic here, but that's not good enough for the proof because the analyticity depends on nu in a very bad way, of course. So therefore, we should not rely on the analyticity in the high norm at all. But with analytic norm, which is based on supremum on some range of parameters inside the domain. So this is the y direction and for fixed x. So then the norm, the analytic norm is L1 based, meaning that we are taking the L1 norms of paths, so just different L1 norms, and that's in the y variable. In the x variable, we take the Gevrey type or Wiener type norms with the analyticity radius in x, which starts at a positive constant, 1 plus mu in this case, and then goes to just 0 up to some 1 plus mu. And again, mu is then a range. So we take a supremum over some mu with the range, and even for the Euler equations, it is known that the analyticity radius does decrease. It's not like artifact of the proof, but one can actually prove that there are solutions where the analyticity radius is decreasing. So we need to take the range of parameters up to a constant which is decreasing in time. And then the norms are the L1 norm with only up to one derivative in dx, and everything is y dy. And then in the interior, oh, this is not interior, sorry, the Sobolev norm in the second derivative has to come up with a weight, and that's technical reasons comes from at the end of the proof. But so note that this norm allows the vorticity to be large. So initially we had the L infinity norm, which keeps the vorticity bounded, but L1 allows the vorticity to grow over this. And this is kind of consistent with some known criteria, sufficient criteria of Kato's type. For example, the paper with Constantine, Vicol, Lopez. I'm sorry, I missed one of the authors. So where the L1 of the vorticity norm seems to play a role in the weak convergence, at least for the Euler equations. So anything allows the growth, anything less than L1. For the Sobolev, one just takes the weighted L2 norm up to basically the norm is H3, but the initial data turns out to be H4. But the initial data for the interior turns out is H3, but although we did not try hard to optimize. So the full norm is then to the sum of the L1 analytic norm and the L infinity norm. So there are two results. So the first is the uniform bounds. So given the initial data, if the initial data is analytic, and if there is Sobolev in the interior with H4, if it's bounded by constant, then the total norm is uniformly bounded for positive time up to a constant depending on m, but not depending on the viscosity. So if in the vanishing viscosity theory you have a bound on very strong norms, you have a hope for the inviscid limit to hold. And indeed, if omega naught is in the statements, analytic and Sobolev, then the U converges to U bar in the L2 norm as nu goes to 0. Actually, the proof of this last part, how does the first part imply second part, is presentable. So I'll show it to you right now. And then just comment a bit on the ideas behind this, and then we'll see if I have time for some parental. So proof of the inviscid limit statement, the second statement given the first statement. So assume that the uniform bound holds. Then in view of the Kato's criterion, we only need to estimate the total energy dissipation in a small boundary layer of the size nu, but we can as well estimate in the full half space. This may seem to be a problem. However, first of all, in Kato, the two conditions are equivalent. So having close to the boundary is equivalent having this. And second, if you have very strong uniform bounds in the interior, then as soon as you're away from the boundary, let's say constant size, then this nu actually makes things go to 0. So, but in any case, we can prove this. The full norm is a little O of 1 as nu goes to 0, meaning it goes to 0. The first step is to prove this. This I'll not show, but it's this follows from the mild formulation of the Navier-Stokes equations, which I'll speak in a moment. So in the first step, you need to go from the L1 bound to actually the L infinity bound, but which is kind of large. It's of the size 1 over square root of nu, so it's not uniform. Okay, so and then we take the Kato's dissipation of energy term. We split it. We split it's same as the same with the vorticity. We split it into the range close to the boundary and away from the boundary. Away from the boundary, you just bound with Sobolev norms, and this nu prevails and makes the second term controllable. It's actually better than the final bound. So we only have to look like what is happening close to the boundary. So there we have the L2 norm. So we basically interpolate L2 between L infinity and L1. So we use one of the omegas to just bound it by 1 over square root of nu. And this time turns out to be harmless, looks bad, but it's a square root of square root, and happily that's there is enough uniformity. So we go to the L1 norm. The L1 norm is bounded by the L1 analytic norm. We can just add this exponential term in, and we obtain 1 over square root of nu s times this. And this is uniformly bounded, and 1 over s is 1 over square root of s is integrable, where nu is powerful enough to control the square root of nu. And we obtain the Kato's quantity goes to 0 with the rate square root of nu. So returning to the Kato's criterion, you can actually even get the rate of convergence, which is O of nu to the quarter for the inviscid limit. Again, the inviscid limit in stronger norms cannot hold. So you can get in L2, and then you can actually even obtain the bounds in LQ for Q bigger than 2. But maybe a few words about the mild formulation and some ideas of the proof. The mild formulation is due to Nguyen and Wang paper in which the need for the parental corrector was removed. So applying the curl to the Navier-Stokes equations, you obtain the usual curl formulation of the Navier-Stokes. However, the boundary conditions for the vorticity are a little bit unpleasant, and they were the main tool used by Maekawa. So there is a vorticity boundary condition, and it's of Neumann type. So if you forget this term, it's a new dy. And on the right side is the term resulting from the nonlinearity. So we need to take the Dirichlet inverse of the u dot grad nu, and then dy and evaluate the boundary. So these are the boundary conditions which were successfully employed by Maekawa in his proof of the local vorticity result. So these boundary conditions follows from the formulation that dt u1 is 0. So you use that equation, the BSR rho for the vorticity equation, if you'd like to prove this. So this is the vorticity formulation for the half space, and the integral representation of this was introduced by Wang. So we denote n to be the nonlinearity. The b is the boundary nonlinear term. So then we can write the vorticity equation in this form. So dt omega minus nu Laplacian omega is this nonlinearity, and the boundary term is this. So then denoting the Green's function of this problem by G, then omega, so the vorticity can be obtained from the initial data term, the interior term, and the boundary term. So and to bound the Green's function, we use the bounds by Wang from 2018, which are stated here. So the Green's function can be decomposed into two parts. One is the Neumann Green's function for the half plane, plus the residual part. And the residual part, so this is clear. So it's like a Green's function for the full space. It's kind of treated the same way. And the residual part does not have viscosity in it in the same way as this one does, but it's hidden in this B. So the derivatives of R are Neumann of similar type as the Neumann Green plus a part, another part. So one has to treat these two things kind of differently. But they kind of seem to be of the same size, even though they're of completely same, different looks. All right, so that the proof then consists of 4 parts. So we first estimate the y-analytic norm of the nonlinear part. For this, we need to split into 2 parts, the analytic part and non-analytic part. In each one, we estimate in one part, again, with analyticity and one with Sobolev regularity. Then we need to do the same for the boundary term. The estimates are completely different, but turn out to be qualitatively same as in the interior, meaning you have to treat terms quite differently, yet the bounds are of the equal strength. Then we need to obtain bounds for the analytic and Sobolev norms of the nonlinearity. The analytic norms of the nonlinearity contain the velocity and the vorticity. So we also need to bound the velocity using BSR laws with omega. And again, in these norms. Then in the 4th step, one does the local Sobolev estimate for omega. So to do local estimates for omega, of course, they don't close. So it's not possible to close interior estimates for evolution equations without using boundary conditions. So what happens is when you are doing the local estimate, you obtain you need to look at the parts which is between. So this is the Sobolev regions, and then when you do local estimates, you get half of the analytic region where you need to do upper bounds. So we need to actually take this region and bound it using the analyticity. So the local Sobolev estimates are done here, they're close, but the lower order terms turn out to be supported away from the boundary where analyticity can be used. It's difficult to use analyticity close to the boundary because growth of vorticity is allowed. It's like 1/square root of nu. So that's why this it's important to bound it like constant distance away, and then gathering all the bounds and using the norms at hand. More recently, we have obtained the parental expansions for the Navier-Stokes equations in these same norms. So analytic close to the boundary, Sobolev away. So the vorticity for the Navier-Stokes minus the vorticity for the Euler and the vorticity for the parental is bounded by O of epsilon. So this improves the rate of convergence for the parental expansions if you're using the analytic norms, L1 analytic norm and Sobolev norm to the boundary. So here, to obtain this, one needs to take those error equations, which I stated several slides before, and apply things on it. So it's quite a lot of terms. The other difficulties are the non-vanishing of the error equations to the boundary. So one needs to change the Biot-Savart laws and apply all the estimates on that. The important thing of the Euler equations is the property that the Euler equations preserve analyticity close to the boundary. So if you have Euler equations and it's analytic close to the boundary and Sobolev away, then it remains like this, although the analytic norm can be shrinking close to the boundary. This is an old result of Bardos and Benachur, but we had an energy-based norm in the paper. So yeah, by the way, here this is what we call the boundary layer vorticity. Sometimes people use this as a vorticity, so we use sometimes people use this as a vorticity. We perturb this; it's more natural, so we get a much more natural looking result. Maybe a few words about the parental equations, which are always in the background. So even though the inviscid limit result as presented does not use parental, so we prove that this quantity is uniformly bounded, the proof is actually consistent with the parental expansions because of this result here. Namely, one can prove that this is uniformly bounded, and on top of it, that the parental expansion error converges to 0. So the parental equations, even though they don't come explicit in the proof, are still controlling the dynamics. So let me say a few words about the parental, and then I'll complete. So the parental equations in 2D read. So read as stated before. So we have the heat part, but only in the y variable, and in the inertial part, the pressure is given, and there is no right side. So the boundary conditions are vanishing at the boundary. So there is no evolution equation for V, and V is computed from U based on the divergence-free condition, as shown here. So it seems like one derivative loss, and this type of derivative losses need to be overcome by analyticity. And this is the known well-posedness theory. In 2D case, Oleinik in '66 proved existence for monotonic Sobolev data, and Masmoudi Wang found the energy-based proof, much simpler proof for existence for monotone data. So Keflish and Sammartino, they proved existence for analytic data, it's analytic in X and Y, and the main device was the abstract Cauchy-Kovalevsky theorem. So then with Canon and Lobardo Sammartino, they proved analyticity with respect to X only. So assuming only analyticity in X only and exponential decay in Y, then local existence. So with Vlad, we obtained energy-based proof. And additional benefit of which is that one can actually combine the monotone and the analytic data into data which are in some regions monotonic, some analytic. So they can go basically up and down. And only when they're changing sign, you assume analyticity. It's a little bit more complicated than that because in the interior, it's the function is, of course, function of two variables. So it's not so general, but indeed for analytic and monotone regions. As I think I have it I don't have it here. That's the result with Masmoudi, Wang, and Vlad. Very surprisingly, it turned out that actually the Prandtl equations are well posed in Gevrey too. And even though we have a one derivative loss, and that's the result by Dieter and Girard-Varret. And the idea is somehow to take another derivative of the equation, and that seems to save a derivative because we are looking at the second order equations with the one derivative loss. But of course, the proof is much more complicated than that. So the ill-posedness theory, which maybe gives us a hint of troubles ahead for the inviscid limit problem. So there are instability results. Then E and Enquist, they proved the finite time blow up of smooth solutions with for zero Euler flow, and with Vlad and Fay, now it's already a while ago, we proved that that solutions blow up for odd data, for a large class of odd data. So odd data are important because you get a stagnation point or flow going against each other, which seems to be the main problem for the inviscid limit too. So the inviscid limit should fail when there is velocities coming from different sides, creating the vorticity which would then propagate into the interior and mess things up. So so I don't have much time to discuss the inviscid limit problem, but maybe it's a good time to stop.
Sorry,
Yeah,
I have to give you the 1 minute warning, but
oh, I see.
Sorry about this.
Oh, no, it's okay. I was planning to stop at some point. So thank you. So yeah, maybe I'll state the theorem and leave it like this. So there exists a family of analytic initial data, and the data is could be any kind which is sort of odd. It is maybe nice to say an open problem. So for non-odd data, as far as I know, the blow-up has not been constructed. So that would be maybe an interesting challenge. So something which velocity is going toward each other, but not necessarily odd. So yeah, so thank you very much. I'll stop here. So thank you. Attention.
Thank you very much, Igor. Is there any questions?
I would have a question if you don't mind.
Sure.
Please, Peter.
So great talk, a lot of stuff. My question is maybe many prompts.